Lowering numeric precision makes a model easier to store, but it does not make the model architecture smaller. Distillation takes a different approach. It trains a smaller student model to reproduce useful behavior from a stronger teacher. I'm Mehrdad. In this lesson, we will explain the training signals, compare modern methods, cover reasoning step transfer, and decide when distillation is preferable to quantization or training from the beginning. Imagine that a large model has been quantized until it fits comfortably in memory. Supported kernels may even make its computation faster. The server still runs every layer and every parameter in the large architecture, so token latency may remain too high for the product. The model may also carry broad capabilities that the application never uses, while its behavior on one narrow task remains difficult to control. Distillation changes the model rather than only changing its numeric precision. A smaller student has fewer parameters and requires less computation for each token. Training then focuses that limited capacity on the behaviors selected from the teacher. This approach can reduce latency and simplify deployment when the task is narrow enough for a smaller model. It also introduces training cost and the risk of copying the teacher's mistakes. The rest of this lesson explains how that transfer works and how to evaluate it. If this explanation is useful, like the video and subscribe to follow the series. Distillation begins with a teacher that performs the target task well and a smaller student that is less expensive to serve. The teacher can provide two main training signals. The first signal is a probability distribution over possible next tokens. This distribution is called a soft target because it shows not only the preferred token, but also how the teacher ranks alternatives. A hard label reveals only one accepted answer. The second signal is generated training text, such as answers, explanations, or task demonstrations produced by the teacher. The student can learn from soft targets, generated text, or a combination of both. During training, the student updates its own weights to make its outputs closer to the teacher's behavior on selected tasks. The teacher normally remains fixed. This process does not guarantee that every teacher capability transfers into the smaller model. Student capacity, training prompts, output diversity, and the loss function all affect the result. Choose the behaviors first, collect teacher signals that cover those behaviors, train the student, and evaluate the student on the deployed tasks. The first method choice is how the training loss compares the student's token probabilities with the teacher's probabilities. Standard soft knowledge distillation asks the student to cover the probability mass assigned by the teacher. This gives the student information about many possible tokens, including alternatives that are not selected in the final teacher response. For text generation, covering every alternative can sometimes spread the student's probability across too many mediocre continuations. A reverse KL objective changes the direction of the comparison. It penalizes the student when it assigns probability to continuations that the teacher considers unlikely. The result tends to concentrate the student on answers that the teacher strongly prefers. MiniLLM applies this reverse direction objective to generative language model distillation. Neither direction is automatically better for every task. Standard soft distillation may preserve more of the teacher's full uncertainty, while the reverse objective may produce sharper generations. Compare them on the behavior that matters, including factual answers, diversity, formatting, and failure rates. The next choice is which text the student sees during training. A fixed teacher-generated dataset is called off-policy data because the examples do not come from the student's current behavior. This approach is simple and reusable, but it may not include the mistakes the student makes after deployment. On-policy training asks the current student to generate responses, then uses the teacher to evaluate or guide those student responses. The training data therefore changes as the student changes. Methods such as GKD and DistiLLM use this idea so training focuses on sequences the student is actually likely to produce. This can reduce the gap between training examples and served outputs. Generating new student responses and scoring them with the teacher is expensive, especially for large datasets. Practical recipes may mix fixed teacher examples with recent student samples or reuse earlier samples for several updates. The decision is not simply old method versus new method. Choose how much student-generated data you need to expose real student errors without making teacher inference and training costs too large. A single teacher target tells the student what to imitate, but it may not show clearly which alternatives should be avoided. Contrastive distillation trains from comparisons between stronger and weaker responses. The student learns to increase the probability of responses judged closer to the teacher's desired behavior and decrease the probability of weaker alternatives. DistiLLM-2 uses this comparative signal for language model distillation. The useful intuition is similar to learning from a positive and a negative example at the same time. The quality of those comparisons matters. If the stronger response is mislabeled or the weaker response differs for an irrelevant reason, the student can learn the wrong distinction. Build response pairs from an irrelevant reason. The student can learn the wrong distinction. Build response pairs from an irrelevant reason. The student can learn the wrong distinction. Build response pairs from an irrelevant reason. The student can learn the wrong distinction. Evaluate complete generated answers rather than only the training loss. A contrastive objective is valuable when choosing among plausible responses matters, but it does not replace accurate data, representative prompts, or task-specific evaluation. Teacher-generated answers can include intermediate solution steps rather than only a final response. These step-by-step examples give the student additional training tokens that connect the question to the answer. A smaller student may learn useful problem-solving patterns from those traces, even though it has fewer parameters than the teacher. The process is still supervised training on teacher-generated data. It does not guarantee that every written step reflects the teacher's actual internal computation, and a convincing explanation can still contain a false step. Data rights also matter because the training pipeline must be allowed to store and reuse the teacher's generated text. Before using reasoning traces, filter incorrect solutions, remove unsafe content, and verify that the steps lead to the supported answer. Evaluate both final answer accuracy and the correctness of the produced steps when users will see or depend on them. Use traces when they improve the target task, not because longer responses automatically provide better supervision. Distillation is one way to obtain a smaller model, but it is not always the best starting point. Training from the beginning may be preferable when you have a large clean dataset, sufficient compute, and no reliable teacher access. Continued pre-training followed by task fine-tuning can also adapt an existing small model without copying a teacher's complete output behavior. Distillation becomes attractive when a strong teacher already demonstrates the required task and teacher-generated data can be used legally. The second comparison is quantization. Quantization usually keeps the large architecture and stores or computes its values with fewer bits. Distillation changes the parameter count and computation required for every token. Choose quantization when the large model already meets the behavior target. Supported hardware accelerates the format, and the main problem is memory or serving cost. Choose distillation when the product needs lower latency, a smaller deployment, or behavior focused on a narrower domain. The methods can be combined. After training a smaller student, you can quantize that student and evaluate the additional quality loss. A student can reproduce the teacher's strengths, but it can also reproduce the teacher's errors more cheaply and at greater scale. If the teacher invents identifiers, produces unsafe advice, or follows the wrong tool format, those examples can teach the student the same behavior. Filter teacher data and retain records of which teacher, prompt, and settings produced each example. Licensing is a separate release requirement. Confirm that the teacher's terms and the source data licenses allow generated outputs to be stored and used for training. Evaluation must then match the student's intended role. Average benchmark scores may hide failures in domain terminology, tool arguments, code, safety behavior, or exact identifiers. Compare the student with the teacher, the original small model, and the production baseline on the same task set. Check whether the student amplifies a teacher weakness, even when its average score looks acceptable. Distillation transfers selected behavior, so the release process must verify exactly which behavior was transferred. Choose the serving method by identifying the actual bottleneck. If the large model already produces the required behavior but barely fits in memory, Quantize it using a format supported by the hardware. If aggressive quantization breaks important tasks, use a higher precision or recover the same model with quantization-aware training. If the architecture itself is too slow or too expensive, train or distill a smaller model. If requests vary greatly in difficulty, route simpler requests to the smaller model and reserve the larger model for cases that need it. Routing requires a reliable way to estimate difficulty and a fallback when the small model is uncertain. If every model meets the quality target but traffic exceeds available throughput, additional serving capacity may be the simplest answer. Measure quality, latency, memory, training cost, and operational complexity for each option. Do not select a method because its name is newer. Select the smallest change that addresses the measured limit while preserving required behavior. Quantization and distillation reduce different parts of serving cost. Quantization changes numeric precision, while distillation trains a different model with fewer parameters. Both methods require task-specific evaluation before deployment. In video 14, we will move from model compression to the information placed inside the model's context. We will examine how to allocate limited context space across instructions, examples, retrieved evidence, and conversation history. I'm Mehrdad, and I'll see you in the next video.